In this video, we will explore hierarchical paging, a technique used in modern operating systems to manage memory efficiently. We will delve into multi-level page tables and their numerous advantages, offering a comprehensive understanding of this essential concept. Let's begin. Let's understand the problems with single-level page tables. Single-level page tables consume a large amount of contiguous memory, which becomes a problem in modern systems. Modern address spaces are very large. For example, 64-bit systems can address a huge amount of memory. However, most processes only use a small fraction of their address space, leading to a lot of wasted memory when using single-level page tables. As you can see in the diagram, single-level page tables lead to wasted space because most entries are unused, requiring large address space, for example, 4 gigabytes to 4 terabytes. Hierarchical paging is a memory management scheme that divides the page table into multiple levels, creating a tree-like structure to make efficient use of memory. It breaks large page tables into smaller, manageable pieces. Only page tables are allocated for address ranges that are actually in use, which significantly reduces the memory overhead for page tables. As shown in the illustration, the root page directory points to level 1 directories, which in turn point to page tables. The unused portions are not allocated, saving memory. In a two-level paging scheme, the virtual address is divided into 3 parts. P1, which is the index into the outer page table. P2, which is the index into the inner page table, and D, the offset within the physical page. This division allows the system to allocate page tables only for the parts of the address space that are actually used. Let's look at the pseudocode for the address translation process. The translate address function takes the virtual address as input, extracts P1, P2, and D from the virtual address. It then uses P1 to find the corresponding page directory entry. From there, it gets the page table address. Then it uses P2 to index into the page table and retrieve the frame number. Finally, it returns the physical address by combining the frame number and offset, D. Here's an illustration of the two-level paging address structure. A 32-bit virtual address is divided into 3 parts, P1, P2, and D. P1, which has 10 bits, is the index for the page directory. P2, which has 10 bits, is the index for the page table, and D, which has 12 bits, is the offset. To translate the address, first, P1 selects an entry in the page directory, which points to a page table. Then, P2 selects an entry in the page table, which points to a physical frame. Finally, D selects the specific byte within that frame, resulting in a physical address. The physical address is constructed by combining the frame number, obtained from the page table, shifted left by 12 bits, with the offset D. Hierarchical paging offers several key benefits. First, it provides memory efficiency, allocating page tables only for the portions of the address space that are actually in use. It provides scalability, supporting very large address spaces, such as those found in 64-bit systems. Hierarchical paging also offers flexibility, allowing different regions of memory to have different protection levels. It simplifies the implementation of shared memory between processes, and it reduces fragmentation, leading to better management of physical memory allocation. As shown in the diagram, hierarchical paging significantly reduces memory wastage compared to single-level page tables. Despite its advantages, hierarchical paging does have potential challenges. One major challenge is the increased memory access time, as multiple memory accesses are required for address translation. Additionally, it adds complexity to page table management and can increase cache pressure due to more memory references, potentially leading to more cache misses. To mitigate these challenges, translation look-aside buffers, or TLBs, are used to cache recent translations, and hardware support is implemented to optimize multi-level page table walks. The TLB acts as a cache that stores recent translations, which allows the CPU to quickly retrieve the physical address without walking through multiple levels of page tables. Hierarchical paging is widely implemented in modern operating systems. The x86-64 architecture uses 4-level paging by default, with support for 5-level paging. Linux implements multi-level page tables with architecture-specific optimizations. Windows uses multi-level paging with different structures for 32-bit and 64-bit systems. ARM64 implements 3 or 4 levels of translation tables, depending on the configuration. The code snippet shows the Linux x86-64 page table entry structure, which contains fields like present, writable, user access, accessed, dirty, and the physical address, controlling various aspects of memory management. Let's summarize what we've learned. Key concepts include hierarchical paging, which divides page tables into multiple levels, virtual addresses, which are split into multiple indices and an offset, and the allocation of page tables only for the portions of the address space that are in use. The advantages of hierarchical paging include significant memory savings for page tables, support for very large address spaces, and flexible memory protection and sharing capabilities. The challenges include multiple memory accesses for address translation and increased complexity in page table management. Solutions such as translation look-aside buffers, hardware support for page table walks, and optimized page table structures are employed to address these challenges. In conclusion, hierarchical paging represents a critical advancement in memory management, enabling modern operating systems to efficiently handle large address spaces while minimizing memory overhead. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.